So this video is about division. We're going to be dividing whole numbers, numbers in decimal form, and numbers in fractional form. So, division with whole numbers. Let's take 54 divided by 9. So, one way to think about this is to do repeated subtraction. So, this isn't a new idea. I talked about this in the sort of what is division and some visual representations of division. So, let's do repeated subtraction. So we start with 54 and we subtract 9. That gives us 45. And then we subtract 9 again. So we get 36. Subtract 9 again, we get 27. Subtract 9 again, we get 18. Subtract 9 again, we get 9. Subtract 9 again, we get 0. So how do we figure out what our answer is? Well, it's how many times you subtracted 9. So 1, 2, 3, 4, 5, 6. So we subtracted 9 exactly 6 times, so 54 divided by 9 is 6. Now, very similar to this, if we turn this division question into a multiplication question, 54 divided by 9 equals what? We can rewrite that as 9 times what equals 54. Multiplication is repeated addition. So now, we're going to start with 9, and then we're going to add 9s until we get to 54. So 9 plus 9 is 18. Plus another 9 is 27, plus another 9 is 36, plus another 9 is 45, plus another 9 is 54. And we're again going to look at then how many 9s did we add. So I had 1, 2, 3, 4, 5, 6. So it takes 6 9s to make 54, so 54 divided by 9 is 6. Another way to think about this is to take 54 and to break it into 9 groups. So here is one of the methods that I use to keep track of this. So I use G to stand for group. I know, creative, right? So I have group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, and group 9. And now I'm going to take 54 and I'm going to pass it out to each of those groups. So let's say I start by giving every group 5. So that's what I've done here. So group 1 got 5, group 2 got 5, group 3 got 5, etc. Now, I need some way of keeping track of how much I've passed out and how much I have left, so I tend to write it over to 8. So if I gave 5 to every group, that's 5, 10, 15, 20, 25, 30, 35, 40, 45. So I gave out 45. If I have 54 and I gave out 45, that means I have 9 left. So to get that, I do 54 minus 45, and that gives me my 9 left. So now I need to keep passing them out. Well, I have 9 left and I have 9 groups. So let's give 1 to every group. So again, group 1 got 1, group 2 got 1, group 3 got 1, etc., etc. So now I gave out 9 more. So I had 9 after the first round, so I gave 9 out, so now I don't have anything left, so I have nothing left. So then my answer is, how much is in each group? So if I look at each group by itself, each group got a 5 and a 1, which means every group got 6. So each group has 6, therefore 54 divided by 9 is 6. Okay, take 54 and split it into groups of 9. Well, this is exactly like repeated subtraction or the repeated addition with the think multiplication. So I'm really trying to figure out how many 9s are inside of 54. So there was a couple ways to do that. So remember, we did 54 and then we subtracted a whole bunch of 9s. If I subtract 6 9s, I get 0. Or if we do the adding, so that I take 6 9s, I add them together, I get 54. So then that tells me that 54 divided by 9 is 6. Okay, another example, division of whole numbers. And on the last one, I showed you several different ways to do the division or to think about the division. And one of the challenges that you're going to have is trying to pick the best way for the computation at hand. So for example, let's take 138 divided by 46. One way to do this is to use objects. Well, I don't know about you, but there's no way I'm going to draw out 138 objects. That will work, right? But I'm not going to do it. Now, I could draw something that had an area of 138. Again, possible, too big, I'm not going to do it. Okay. Now, 46 groups. Well, that technique made sense for the last problem when I only had 9 groups, but 46 groups seems like an awful lot. I don't want to have to write G1, G2, all the way up to G46. So that one isn't really going to make sense in this particular case. Now, how many 46s are there in 138? This is the one that's going to make more sense. So one way to interpret that is to think of groups of 46, or to think of repeated subtraction, or to think multiplication and use repeated addition. Now, any of those methods would work fine here. Now, if I use repeated subtraction, 138 minus 46 is 92. 92 minus 46 is 46. 46 minus 46 is 0. So I need to keep track of how many times I subtracted 46. So here was a minus 46, here was a minus 46, here was a minus 46. So I subtracted 46 3 times. Or if I'm thinking of the addition, 46 plus 46 is 92. 92 plus 46 is 138. So I added 46 3 times. So either of these methods are going to tell you that there are 3 46s inside of 138, which means 138 divided by 46 is equal to 3. Another one, 624 divided by 4. Now, I could do repeated subtraction or repeated addition. It would work, but then I'm doing 4 plus 4, which is 8, plus 4, which is 12, plus 4, which is 16. Well, I have a long way to go to get up to 624. So repeated subtraction in this case might not be the best option. So I would probably say no to that one. Groups of 4. Again, this is really related to the repeated addition and subtraction. So again, I'm going to say no to that, because then I'm just taking 4 and then 4 and then 4. So it's going to take me too long. Now, what about 4 groups? Okay, well now, G1, G2, G3, G4, 4 groups. All right, maybe that makes a little bit more sense. So I'm going to start with my 4 groups. And I'm going to start, in this case, I'm going to pass out 100 to each group. I know I have 624, and I need to break that into 4 groups. So I know that every group gets at least 100. Now, if you start by dividing it by a different number, you give every group 50, or you give every group 80, or you give every group 120. It's totally up to you, whatever you see first. So I went with 100 because I thought it was a good place to start. So that means that I passed out 400. So that's where this number is coming from. So I take my 624, I subtract 400. That tells me I have 224 left to pass out. So let's try it again. So let's try 50. So I pass out 50 to every group. That means I passed out 50, 100, 150, 200. So I passed out 200. So I take the 224 and I subtract 200, which tells me I have 24 left to pass out. Well, maybe at this point you've gotten the number small enough where you're like, oh, well, 24 can be divided easily by 4. Okay, or maybe you pass out 5s, maybe you pass out 3s, whatever it is that you see. So I noticed that 24 is divisible by 4, so I passed out 6 to every group. So just to make sure I'm keeping track, I had 24 left over, so that's this 24, and then I passed out 6, 12, 18, 24, that's this 24. So I had 24, I passed out 24, so now I don't have anything left. And then looking at my groups then, every group has 156. So all the groups are even, and I passed out all of the 624, so there's my 156. Now, some of you might be asking, well, why are we doing this grouping thing? We have this nice algorithm, right? Why am I using up more ink or more graphite to write all of this down? I have this very succinct algorithm for long division, such as it's called, right? So why are we doing it this way? So let's look at the long division. So this is how we set it up. So here's 624 inside the house, and the 4 is outside the house. And then we start to walk our way through this. So we look up the 4, and we look at the 6, and we say, all right, well, here's 4, and here's 6. Well, 4 goes into 6 one time. So I put that 1 up top. but that's not really just a 1. Okay, if you pay attention to where that's being placed, notice the 1 is placed on top of the 6. So that 1 is not really a 1. That 1 is actually 100. Look over here. That's exactly what I did. I passed out 100 to every group. Okay, back to our algorithm. So 4 goes into 6 one time, and then we do this crazy 1 times 4, and we write it underneath, and then we subtract it, and we end up with 224. So now we took 400, we subtracted it, and we were left with 224. And then we start the process over. So we go 4, this 4 into 2, but it doesn't go into 2, so then you're supposed to look at 22. So 4 goes into 22 5 times, so the 5 goes up top. But again, that's not really a 5. Notice where it was placed. It's placed above this 2, which means it's in the tens place. So that's actually a 50. And if we come over here, 50, 50, 50, 50. Then we take the 5, we multiply by 4, so there's our 20, or to keep all of our place values, our 200. So then we subtract 200, which leaves us with 24. So we subtract 200, that leaves us with 24. And now we're all the way over in the ones place. So 4 doesn't go into the 2 of the 24, but 4 goes into 24 6 times. So we write the 6 up top. 6 times 4 is 24. We subtract it, we get 0. So this 6 that we put up here is actually a 6 in the ones place, which corresponds perfectly to the 6 that we had over here. So the algorithm that we use, this particular algorithm, which often looks like, I have no idea why we do this. We do this number into this number, and then we write it up top, and then we multiply these numbers, and we put it down underneath, and then we subtract, and then we do it again. It feels a little bit convoluted or separated from the idea of division, but I think it's really cool to notice that this idea of breaking 624 into 4 groups is exactly what long division does. All of those little steps are there, right? We put the 100 for the 1 here, and then we subtracted 400, which gave us 224. Okay, and then we did the 5 up top. Well, that's the 50 here. And then we subtracted 200, which left us with 24. So it's a perfect parallel. Now, an advantage to the grouping method is that with the grouping method, you can group in any order you want. Okay, so for example, if I had looked at 624 divided by 4, and I noticed that right off the bat, I could put 150 into every group, then I could jump right to 150 per group. Or maybe I thought, well, I don't really know, so let's try 120. So you put 120 in every group. Great. Or maybe you wanted to start with 70, or maybe you want to start with 50. Okay. With the grouping method, you can choose whatever denominations you want to put into every group, as long as it's equal into each group. The algorithm, on the other hand, is very, very specific. You have to put the maximum number of hundreds, and then the maximum number of tens, and then the maximum number of ones to make it work. But they're the same. Okay, so let's talk about some division questions with decimals. And again, we're going to use some models here. So let's talk about what model might be appropriate for a question like this. So 23 and 8/10 divided by 3 and 4/10. If I were going to use an area model, I would need to start by drawing 23 and 8/10. Well, that's possible, but I don't think I want to draw 24 boxes, the 23 whole boxes, and then the 8/10 last box. So then I might want to look at, okay, what about 3.4 groups? Well, that doesn't even make any sense to me. How do I have 3 and 4/10 groups? So we're not going to do that one. What about groups of 3.4? okay, groups of 3 and 4/10. Okay, that makes sense to me. Okay, or that's really the same as asking how many 3.4s are inside of 23.8. So we've talked about that the two main ways to do this are repeated subtraction. Start with your 23 and 8/10 and subtract 3.4 as many times as you can, or start by adding 3.4 as many times as you can to get up to or close to 23 and 8/10. So repeated subtraction. So it's going to take a couple of subtractions to get through this. So I put it up at the top. So we subtract 3 and 4/10, and then we subtract it again and again and again and again and again and again. And so if we look, we subtracted 3.4 1, 2, 3, 4, 5, 6, 7 times. So not necessarily the quickest way to do it, but pretty efficient. Okay, so 23 and 8/10 divided by 3 and 4/10 is 7. Just to show you the repeated addition, here's 3 and 4/10 plus 3 and 4/10 plus another 3 and 4/10 plus another plus another plus another and then another, and that takes me to 23 and 8/10. So we're looking at how many 3 and 4/10 we added. 1, 2, 3, 4, 5, 6, 7. So 3 and 4/10, we added it 7 times to get 23 and 8/10. So that tells us that there are 7 3 and 4/10 inside of or in 23.8. So 23 and 8/10 divided by 3 and 4/10 is 7. Okay, also nice with decimals to use an area model if the numbers are small enough, but also not too small, right? We like the 10 by 10 grids because they very nicely show the ones digit, they very nicely show the tenths place, and they very nicely show the hundredths place. Not ideal for numbers that go smaller than hundredths, and like on the example before, not always great if there are numbers in the tens place, just because it's going to mean a lot of drawing. But this particular example, both of these numbers have tenths and hundredths in them, so we're going to go ahead and do this. So 72 hundredths divided by 24 hundredths means we need to start by drawing the 72 hundredths. So I almost always start with a 10 by 10 grid, and then I shade in my 72 hundredths. So you can think of that as 72 little boxes, or you can think of that as 7 columns and then 2 boxes on the edge. So now I want to know how many 24 hundredths is in there. So I can interpret 24 hundredths as 24 boxes, which would work, or I could think of this as 2 columns plus 4 boxes. Either way is fine. So let's start to group or figure out where these 24 hundredths are. So here's my first one. So notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 little boxes. So that is 1 24 hundredths. Let's find a second one. I'm not going to count on these for you, but then this darker green, that's another 24 boxes. And then the even darker green, that's another 24 boxes. So using area then, I can see that 24 hundredths goes into 72 hundredths 1, 2, 3 times. So 72 hundredths divided by 42 hundredths is 3. So what about a number like this? So here we have 2 and 412 thousandths divided by 6 hundredths. Now, in this particular model, we're not going to want to use area because in this first number, we're going past the hundredths place, which is going to be problematic for us. We probably don't want to use repeated addition or repeated subtraction, especially if we're subtracting just 6 hundredths at a time. Okay, that's going to be difficult to do. It's going to take us a really long time. So what I want to show you on an example like this is to show you what we need to do with our decimals to be able to use long division. Now, this is really important, and it's a huge mistake that students sometimes make. It's a very common misconception, and so it's very important they understand that. If you want to use long division, you must be dividing by a whole number. Okay. Right now, I'm dividing by 6/100. That is not a whole number. I need it to not have anything but zeros after the decimal place. Okay. Long division doesn't work. It screws with your place values if you are not dividing by a whole number. Now, that being said, the number out front, what is being divided, it can keep its decimal. Okay. It doesn't have to, but it can. The key is that what you're dividing by. So when you read this, you say, oh, divided by 6/100. That's what needs to be a whole number. So what are we going to do? We're going to do use what we already know about fractions to figure out how to turn this into a division by whole numbers. So we're going to rewrite this. I just wrote it down below. So this is 2 and 412 thousandths divided by 6/100. Now, another way to write this is to write it in fraction form. The fraction bar means division. Okay, so notice I haven't changed the numbers at all. I just rewrote them as a fraction. And now I'm going to play with this fraction just a little bit. I'm going to use what we already know about equivalent fractions to change this fraction so that I don't have any more decimals in the denominator. And here's how I'm going to do that. I'm going to take the top and the bottom and I'm going to multiply them by 10. And here's what happens. I multiply the top and the bottom by 10. Every time you multiply by 10, remember back to last unit, right? It shifts your place value. So the 2 that was in the ones place is now in the tens place. The 4 that was in the tenths place is now in the ones place. Okay, so I shifted the top number. Same thing in the bottom. The 6 that was in the hundreds place is now in the tenths place. See where I'm going with this? So now what I'm going to do is I'm going to take this new fraction and I'm going to multiply it by 10 again because I still have a decimal in that denominator. When I do that, everything gets shifted one more time. So now I have 241 2/10 divided by 6. Yes, now that denominator is a whole number. So now I can bust out my long division. So my long division will look something like this. The 6 goes on the outside of the house, 241 2/10 goes on the inside, and then we work through long division as we normally would. 6 doesn't go into 2, but 6 goes into 24. It goes in 4 times, right? Notice the 4 got written over the 4 because the 6 was going into 24. And then 4 times 6 underneath is 24. We subtract it. When I subtract it, I end up with 1.2. So now I need to take 6 into 1. 6 doesn't go into 1. Beep, 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 beep. Big alarm going off. Another very common mistake. 6 doesn't go into 1, and so you have to keep track of that. You have to put that 0 up top. Okay, in my opinion, this is one of the reasons that the grouping idea is nice. Okay, instead of using long division, if I had thought of this original question as 241 2/10 broken up into 6 groups, then I wouldn't have had this error. But be very careful. So 6 doesn't go into 1, so you have to put that place value 0. I tend to then subtract the 0 just because it helps me keep track, but if you're comfortable and you skip that part, that's fine. So 0 times 6 is 0, so then I subtract the 0. So I still have the 1 2/10. Now I'm looking at the tenths place. So I'm looking at the 1 and the 2. 6 goes into 12 exactly 2 times. So we put the 2 up top. Then 2 times 6, we multiply that back down. We subtract and we end up with 0. Okay, so what about fractions? So same idea with fractions. Here we have 1 2/3 divided by 1/6. What we're asking is how many 1/6 are inside of 1 2/3. So we could use repeated subtraction. In this case, probably not the best choice just because we're going to have to subtract a lot of sixths to get down to 0. It turns out if you do that, so here I just started the first 2, turns out you can do it 10 times and get there. Or you could also do this with the addition, and that would work too. If we do the addition, again, it's going to take us 10 times to get there, but we'll get there. So, another way to think about it is to think a little bit. Use a little bit of reasoning. How many sixths are inside of 1 2/3? Well, let's think of 1 2/3 as sort of 2 separate pieces. We know there are 6 sixths inside of 1. There are 6 sixths inside of 1. Great. And then we also know that there are 4 sixths inside of 2/3. Now maybe we drew this to figure it out, maybe used equivalent fractions to figure this out, but we can reason our way and figure out that there are 4 sixths inside of 2/3. So putting that together, I can see that there are 10 1/6 in 1 2/3. So using a little bit of reasoning and maybe some drawing, maybe some computation, I can get to this answer without having to memorize a series of steps. Just think about it. How many sixths are inside of 1? How many sixths are inside 2/3? Okay, so then how many sixths are inside 1 2/3? There are 10. So 1 2/3 divided by 1/6 is equal to 10. Now, another way to do these is, you're going to be surprised by this, area models, right? Drawing out what these fractions are to figure out how many sixths are inside of 1 2/3. So, let's draw. So we're going to start by drawing 1 2/3. So I made one rectangle to represent the 1. I needed another rectangle to represent the 2/3. So I split that second rectangle into 3 parts and shaded 2 of those parts. So there's my 2/3. So then the question is, how many sixths are inside of this? Well, in order to do this, I really need to see my sixths. So I'm going to take both these boxes and I'm going to break them into sixths. So notice my whole got broken into 6 parts and my 2/3 got broken into 6 parts. Now, hopefully, it's fairly straightforward to see how many sixths are in here. So here's a 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can see that there are 10 sixths inside of 1 2/3, which tells me, again, that 1 2/3 divided by 1/6 is equal to 10. Now, we can also use this same drawing to find 1 2/3 divided by 5/6. So now I'm not just doing 1/6 anymore, I'm doing 5/6. In other words, I want to find how many 5/6 are in this problem. Well, if I group these together, there's 5/6. And if I group these together, there's another 5/6. So by using this picture, I can see that I have one set of 5/6 and I have a second set of 5/6. So that tells me 1 2/3 divided by 5/6 is equal to 2. Okay, so let's try a bigger question. So now, bigger number. So here's 11 divided by 2 3/4. Now, I could use repeated subtraction or repeated addition. It wouldn't be too bad. I'm looking at a number between 2 and 3, and I'm only going up to 11. So if I were going to estimate this, I know that my answer is going to be around, let's say, 12 divided by 3. So that's not too bad. So the answer is going to be about 4. So repeated addition or repeated subtraction wouldn't be too bad. It wouldn't take me that long to get there. But let's show the area model in this. So now I need to start with 11, right? It's 11 divided by 2 3/4. So I need 11 squares. So this is what I'm going to start with. So I have 11 boxes on here. And now what I need to do is I need to figure out and show that 2 3/4. Okay, well, I could do 1, 2, and then 3/4 of this next square. That would be 2 3/4. And then I could keep going. So let's try that. So I'll clean it up a little bit. So here's my 2 3/4. So notice I have 1, 2, And then in this third box, I broke it up into 4 equal parts, and I shaded 3 of those parts. So that's going to be my 3/4. So far I have 1, 2, and 3/4 fitting inside. Keep going. So I'm going to come over here. I have 1, 2, and then to keep going with my picture, I grabbed this 1/4 and then these 2/4. So there's my 3/4. I'm going to keep going. So now I have 1, 2, 1/4, 2/4, 3/4. Go one more time. So now I have 1, 2, 1/4, 2/4, 3/4. So looking at my picture then, I have 2 and 3/4 exactly 1, 2, 3, 4 times. So 11 divided by 2 and 3/4 is 4. Now, division of fractions. While this is not, what I'm about to show you is not needed in this course, and it is not needed to do division computations, it can be helpful in later algebra courses to understand this algorithm. So you don't have to use this in this class, but I felt like you needed to see it, only because some of the other models get a little bit more challenging if I start throwing variables in there, which is what they're going to do in algebra. Not really until later in algebra will you start doing divisions with variables, but I just felt like you should see this so that you know it's coming. So let's take the example 3/14 divided by 2/7. Now I'm gonna play the game again where instead of writing that division sign, I'm gonna write that division sign as a great big fraction. So for some of you, this looks very intimidating. You're like, oh my gosh, it's fractions inside of a fraction, right? Just think of these as numbers. It does look a little bit big, but this division sign just became this fraction bar right here. So there's my 3/14 divided by 2/7. And now, similar to what we did with taking the decimals and getting them to have a whole number on the bottom, we're going to play a similar game here. I know that to keep this fraction equivalent, again, looking at the great big huge fraction, I can multiply the top and the bottom by any number. Now, I'm going to specifically choose to multiply the top and the bottom by 7/2. And I chose that from here. So I had 2/7 on the bottom, and I'm going to multiply it by 7/2. What happens if I take 2/7 and I multiply it by 7/2? Something pretty cool. 2/7 times 7/2, however you choose to do that, gives me 14/14, which is 1. Dividing by 1 doesn't change a number. So I specifically chose to multiply the top and the bottom of the big fraction by 7/2 so that the denominator becomes 1. So what's happening up on the top? 3/14 times 7/2, that gives me 21/28. So I keep the 21/28. The 14/14 becomes 1. Dividing by 1 doesn't do anything. So this just stays 21/28. Now, I'm fine with that answer. If you need to reduce it or if you would like to reduce it, you can reduce that to 3/4. Okay. You also could have done the reducing here in the middle at this step. If you're comfortable with that, sort of reducing before you multiply, that's fine with me too. Either way is fine. But I do want you to think about this big idea. Okay, I do want you to think about why division becomes multiplication by the reciprocal. Okay, which is how a lot of you have learned it, how a lot of you have memorized it. It doesn't really make any sense why that happens. You just sort of learn this rule that says, oh, division becomes multiplication if you flip the second one over. True, but I would like for you to understand and see where that comes from. Okay, so I took my division, which was here, I turned it into a great big fraction here, and then I just played some equivalent fraction games. And I did it in a very smart and a very deliberate way so that this denominator, instead of being dividing by 2/7, I did it in such a way that that denominator became a 1. Because dividing by 1 means it doesn't change the number. Okay, so in summary, division means how many of one number fits into another number. How many of one number fits in another number? Common mistakes. Decimal long division. You can only use long division with decimals if you are dividing by a whole number. Use your knowledge of fractions, use your knowledge of multiplying by tens to get to a fraction that has a whole number in the denominator, so that you're dividing now by a whole number. Second one, fractions. Don't shortcut the algorithm, okay? Don't just memorize a couple rules and flip and switch them, okay? Think about that big fraction and then how we play with equivalent fractions to turn that denominator into 1.